Carbon dioxide in Earth's atmosphere. Atmospheric CO2 concentrations measured at Mauna Loa Observatory from 1958 to 2022, also called the Keeling curve. Carbon dioxide concentrations have varied widely over the Earth's 4.54 billion year history. However, in 2013 the daily mean concentration of CO2 in the atmosphere surpassed 400 parts per million, ppmv. This level has never been reached since the mid-Pliocene, 2 to 4 million years ago. In Earth's atmosphere, carbon dioxide is a trace gas that plays an integral part in the greenhouse effect, carbon cycle, photosynthesis, and oceanic carbon cycle. It is one of several greenhouse gases in the atmosphere of Earth. The current global average concentration of CO2 in the atmosphere is 421 ppm as of May 2022, 0.04%. This is an increase of 50% since the start of the Industrial Revolution, up from 280 ppm during the 10,000 years prior to the mid-18th century. The increase is due to human activity. Burning fossil fuels is the main cause of these increased CO2 concentrations and also the main cause of climate change. Other large anthropogenic sources include cement production, deforestation, and biomass burning. While transparent to visible light, carbon dioxide is a greenhouse gas, absorbing and emitting infrared radiation at its two infrared active vibrational frequencies. CO2 absorbs and emits infrared radiation at wavelengths of 4.26 micrometers, 2347 cm-1, asymmetric stretching vibrational mode, and 14.99 micrometers, 667 cm-1, bending vibrational mode. It plays a significant role in influencing Earth's surface temperature through the greenhouse effect. Light emission from the Earth's surface is most intense in the infrared region between 200 and 2500 cm-1, as opposed to light emission from the much hotter sun, which is most intense in the visible region. Absorption of infrared light at the vibrational frequencies of atmospheric CO2 traps energy near the surface, warming the surface and the lower atmosphere. Less energy reaches the upper atmosphere, which is therefore cooler because of this absorption. Increases in atmospheric concentrations of CO2 and other long-lived greenhouse gases such as methane, nitrous oxide, and ozone increase the absorption and emission of infrared radiation by the atmosphere, causing the observed rise in average global temperature and ocean acidification. Another direct effect is the CO2 fertilization effect. These changes cause a range of indirect effects of climate change on the physical environment, ecosystems, and human societies. Carbon dioxide exerts a larger overall warming influence than all of the other greenhouse gases combined. It has an atmospheric lifetime that increases with the cumulative amount of fossil carbon extracted and burned, due to the imbalance that this activity has imposed on Earth's fast carbon cycle. This means that some fraction, a projected 20 to 35%, of the fossil carbon transferred thus far will persist in the atmosphere as elevated CO2 levels for many thousands of years after these carbon transfer activities begin to subside. The carbon cycle is a biogeochemical cycle in which carbon is exchanged between the Earth's oceans, soil, rocks, and the biosphere. Plants and other photoautotrophs use solar energy to produce carbohydrate from atmospheric carbon dioxide and water by photosynthesis. Almost all other organisms depend on carbohydrate derived from photosynthesis as their primary source of energy and carbon compounds. The present atmospheric concentration of CO2 is the highest for 14 million years. Concentrations of CO2 in the atmosphere were as high as 4,000 ppm during the Cambrian period about 500 million years ago, and as low as 180 ppm during the Quaternary glaciation of the last 2 million years. Reconstructed temperature records for the last 420 million years indicate that atmospheric CO2 concentrations peaked at approximately 2000 ppm during the Devonian, 400 million years, period, and again, in the Triassic, 220 to 200 million years, period, and were 4 times current levels during the Jurassic period, 201 to 145 million years. Current concentration and future trends. Between 1850 and 2019, the Global Carbon Project estimates that about 2/3 RDS of excess carbon dioxide emissions have been caused by burning fossil fuels, and a little less than half of that has stayed in the atmosphere. Current situation. Since the start of the Industrial Revolution, atmospheric CO2 concentration have been increasing, causing global warming and ocean acidification. In October 2023, the average level of CO2 in Earth's atmosphere, adjusted for seasonal variation, was 422.17 parts per million by volume, ppm. Figures are published monthly by the National Oceanic and Atmospheric Administration, NOAA. The value had been about 280 ppm during the 10,000 years up to the mid-18th century. Each part per million of CO2 in the atmosphere represents approximately 2.13 gigatons of carbon, or 7.82 gigatons of CO2. It was pointed out in 2021 that the current rates of increase of the concentration of the major greenhouse gases, carbon dioxide, methane and nitrous oxide, are unprecedented over at least the last 800,000 years. It has been estimated that 2,400 gigatons of CO2 have been emitted by human activity since 1850, with some absorbed by oceans and land, and about 950 gigatons remaining in the atmosphere. Around 2020, the emission rate was over 40 gigatons per year. Annual and regional fluctuations. Atmospheric CO2 concentrations fluctuate slightly with the seasons, falling during the northern hemisphere spring and summer as plants consume the gas and rising during northern autumn and winter as plants go dormant or die in decay. The level drops by about 6 or 7 ppm, about 50 gt, from May to September during the northern hemisphere's growing season, and then goes up by about 8 or 9 ppm. The northern hemisphere dominates the annual cycle of CO2 concentration because it has much greater land area and plant biomass than the southern hemisphere. Concentrations reach a peak in May as the northern hemisphere spring green-up begins, and decline to a minimum in October, near the end of the growing season. Concentrations also vary on a regional basis, most strongly near the ground with much smaller variations aloft. In urban areas concentrations are generally higher, and indoors they can reach 10 times background levels. Measurements and predictions made in the recent past. Estimates in 2001 found that the current carbon dioxide concentration in the atmosphere may be the highest in the last 20 million years. This figure has been corrected down since then, whereby the latest estimate is now 14 million years, estimate from 2013. Most recently, IPCC AR6, see for example figure 2.34, reports similar levels 3 to 3.3 Maya in the mid-Pliocene warm period. AR6 reports this period as a good proxy for likely climate outcomes with current levels of CO2. Data from 2009 found that the global mean CO2 concentration was rising at a rate of approximately 2 ppm/year and accelerating. The daily average concentration of atmospheric CO2 at Mauna Loa Observatory first exceeded 400 ppm on 10 May 2013, although this concentration had already been reached in the Arctic in June 2012. Data from 2013 showed that the concentration of carbon dioxide in the atmosphere is this high for the first time in 55 years of measurement and probably more than 3 million years of Earth history. As of 2018, CO2 concentrations were measured to be 410 ppm. Measurement techniques. Carbon dioxide observations from 2005 to 2014 showing the seasonal variations and the difference between northern and southern hemispheres. The concentrations of carbon dioxide in the atmosphere are expressed as parts per million by volume, abbreviated as ppmv or just ppm. To convert from the usual ppmv units to ppm mass, multiply by the ratio of the molar weight of CO2 to that of air, I times 1.52, 44.01 divided by 28.96. The first reproducibly accurate measurements of atmospheric CO2 were from flask sample measurements made by Dave Keeling at Caltech in the 1950s. Measurements at Mauna Loa have been ongoing since 1958. Additionally, measurements are also made at many other sites around the world. Many measurement sites are part of larger global networks. Global network data are often made publicly available. Data networks. There are several surface measurement, including flasks and continuous in situ, networks including NOAA/ERSL, WDCGG, and RAMSES, the NOAA/ESRL Baseline Observatory Network, and the Scripps Institution of Oceanography Network. Data are hosted at the CDAC at ORNL. The World Data Center for Greenhouse Gases, WDCGG, part of GAW, data are hosted by the JMA. The Réseau Atmosphérique de Mesure de composes an effet de serre database, RAMSES, is part of IPSL. From these measurements, further products are made which integrate data from the various sources. These products also address issues such as data discontinuity and sparseness. GlobalView CO2 is one of these products. Ongoing ground-based total column measurements began more recently. Column measurements typically refer to an averaged column amount denoted x CO2, rather than a surface-only measurement. These measurements are made by the TCCON. These data are also hosted on the CDIAC and made publicly available according to the Data Use Policy. Satellite measurements. Space-based measurements of carbon dioxide are also a recent addition to atmospheric XCO2 measurements. Sayamaki aboard ESA's Envisat made global column XCO2 measurements from 2002 to 2012. AIRS aboard NASA's Aqua satellite makes global XCO2 measurements and was launched shortly after Envisat in 2012. More recent satellites have significantly improved the data density and precision of global measurements. Newer missions have higher spectral and spatial resolutions. JAXA's GOSAT was the first dedicated GHG monitoring satellite to successfully achieve orbit in 2009. NASA's OCO2 launched in 2014 was the second. Various other satellites' missions to measure atmospheric XCO2 are planned. Analytical methods to investigate sources of CO2. The burning of long-buried fossil fuels releases CO2 containing carbon of different isotopic ratios to those of living plants, enabling distinction between natural and human-caused contributions to CO2 concentration. There are higher atmospheric CO2 concentrations in the northern hemisphere, where most of the world's population lives, and emissions originate from, compared to the southern hemisphere. This difference has increased as anthropogenic emissions have increased. Atmospheric O2 levels are decreasing in Earth's atmosphere as it reacts with the carbon in fossil fuels to form CO2. Causes of the current increase. Anthropogenic CO2 emissions. The US, China and Russia have cumulatively contributed the greatest amounts of CO2 since 1850. While CO2 absorption and release is always happening as a result of natural processes, the recent rise in CO2 levels in the atmosphere is known to be mainly due to human, anthropogenic, activity. Anthropogenic carbon emissions exceed the amount that can be taken up or balanced out by natural sinks. Thus, carbon dioxide has gradually accumulated in the atmosphere and, as of May 2022, its concentration is 50% above pre-industrial levels. The extraction and burning of fossil fuels, releasing carbon that has been underground for many millions of years, has increased the atmospheric concentration of CO2. As of year 2019, the extraction and burning of geologic fossil carbon by humans releases over 30 gigatons of CO2, 9 billion tons carbon, each year. This larger disruption to the natural balance is responsible for recent growth in the atmospheric CO2 concentration. Currently, about half of the carbon dioxide released from the burning of fossil fuels is not absorbed by vegetation and the oceans and remains in the atmosphere. Burning fossil fuels such as coal, petroleum, and natural gas is the leading cause of increased anthropogenic CO2. Deforestation is the second major cause. In 2010, 9.14 gigatons of carbon, GTC, equivalent to 33.5 gigatons of CO2 or about 4.3 ppm in Earth's atmosphere, were released from fossil fuels and cement production worldwide, compared to 6.15 GTC in 1990. In addition, land use change contributed 0.87 GTC in 2010, compared to 1.45 GTC in 1990. In the period 1751 to 1900, about 12 GTC were released as CO2 to the atmosphere from burning of fossil fuels, whereas from 1901 to 2013 the figure was about 380 GTC. The International Energy Agency estimates that the top 1% of emitters globally each had carbon footprints of over 50 tons of CO2 in 2021, more than 1,000 times greater than those of the bottom 1% of emitters. The global average energy-related carbon footprint is around 4.7 tons of CO2 per person. Roles in natural processes on Earth. Greenhouse effect. Greenhouse gases allow sunlight to pass through the atmosphere, heating the planet, but then absorb and redirect the infrared radiation, heat, the planet emits. CO2 reduces the flux of thermal radiation emitted to space, causing the large dip near 667 cm-1, thereby contributing to the greenhouse effect. Long-wave infrared absorption coefficients of water vapor and carbon dioxide. For wavelengths near 15 microns, CO2 is a much stronger absorber than water vapor. Earth's natural greenhouse effect makes life as we know it possible, and carbon dioxide plays a significant role in providing for the relatively high temperature on Earth. The greenhouse effect is a process by which thermal radiation from a planetary atmosphere warms the planet's surface beyond the temperature it would have in the absence of its atmosphere. Without the greenhouse effect, the Earth's average surface temperature would be about -18 degrees C, -0.4 degrees Fahrenheit, compared to Earth's actual average surface temperature of approximately 14 degrees C, 57.2 degrees Fahrenheit. Water is responsible for most, about 36 to 70%, of the total greenhouse effect, and the role of water vapor as a greenhouse gas depends on temperature. On Earth, carbon dioxide is the most relevant, direct anthropologically influenced greenhouse gas. Carbon dioxide is often mentioned in the context of its increased influence as a greenhouse gas since the pre-industrial, 1750, era. In 2013, the increase in CO2 was estimated to be responsible for 1.82 Wm-2 of the 2.63 Wm-2 change in radiative forcing on Earth, about 70%. The concept of atmospheric CO2 increasing ground temperature was first published by Svante Arrhenius in 1896. The increased radiative forcing due to increased CO2 in the Earth's atmosphere is based on the physical properties of CO2 and the non-saturated absorption windows where CO2 absorbs outgoing long-wave energy. The increased forcing drives further changes in Earth's energy balance and, over the longer term, in Earth's climate. Carbon cycle. This diagram of the fast carbon cycle shows the movement of carbon between land, atmosphere, and oceans in billions of metric tons of carbon per year. Yellow numbers are natural fluxes, red are human contributions, white are stored carbon. Atmospheric carbon dioxide plays an integral role in the Earth's carbon cycle whereby CO2 is removed from the atmosphere by some natural processes such as photosynthesis and deposition of carbonates, to form limestones for example, and added back to the atmosphere by other natural processes such as respiration and the acid dissolution of carbonate deposits. There are two broad carbon cycles on Earth, the fast carbon cycle and the slow carbon cycle. The fast carbon cycle refers to movements of carbon between the environment and living things in the biosphere, whereas the slow carbon cycle involves the movement of carbon between the atmosphere, oceans, soil, rocks, and volcanism. Both cycles are intrinsically interconnected and atmospheric CO2 facilitates the linkage. Natural sources of atmospheric CO2 include volcanic outgassing, the combustion of organic matter, wildfires, and the respiration processes of living aerobic organisms. Man-made sources of CO2 include the burning of fossil fuels for heating, power generation, and transport, as well as some industrial processes such as cement making. It is also produced by various microorganisms from fermentation and cellular respiration. Plants, algae, and cyanobacteria convert carbon dioxide to carbohydrates by a process called photosynthesis. They gain the energy needed for this reaction from absorption of sunlight by chlorophyll and other pigments. Oxygen, produced as a byproduct of photosynthesis, is released into the atmosphere and subsequently used for respiration by heterotrophic organisms and other plants, forming a cycle with carbon. Annual CO2 flows from anthropogenic sources, left, into Earth's atmosphere, land, and ocean sinks, right, since year 1960. Units in equivalent gigatons carbon per year. Most sources of CO2 emissions are natural, and are balanced to various degrees by similar CO2 sinks. For example, the decay of organic material in forests, grasslands, and other land vegetation, including forest fires, results in the release of about 436 gigatons of CO2, containing 119 gigatons carbon, every year, while CO2 uptake by new growth on land counteracts these releases, absorbing 451 GT, 123 GTC. Although much CO2 in the early atmosphere of the young Earth was produced by volcanic activity, modern volcanic activity releases only 130 to 230 megatons of CO2 each year. Natural sources are more or less balanced by natural sinks, in the form of chemical and biological processes which remove CO2 from the atmosphere. Overall, there is a large natural flux of atmospheric CO2 into and out of the biosphere, both on land and in the oceans. In the pre-industrial era, each of these fluxes were in balance to such a degree that little net CO2 flowed between the land and ocean reservoirs of carbon, and little change resulted in the atmospheric concentration. From the human pre-industrial era to 1940, the terrestrial biosphere represented a net source of atmospheric CO2, driven largely by land use changes, but subsequently switched to a net sink with growing fossil carbon emissions. in 2012, about 57% of human emitted CO2, mostly from the burning of fossil carbon, was taken up by land and ocean sinks. The ratio of the increase in atmospheric CO2 to emitted CO2 is known as the airborne fraction. This ratio varies in the short term and is typically about 45% over longer, 5-year periods. Estimated carbon in global terrestrial vegetation increased from approximately 740 gigatons in 1910 to 780 gigatons in 1990. Photosynthesis. Photosynthesis changes sunlight into chemical energy, splits water to liberate O2, and fixes CO2 into sugar. Carbon dioxide in the Earth's atmosphere is essential to life and to most of the planetary biosphere. The average rate of energy capture by photosynthesis globally is approximately 130 terawatts, which is about 6 times larger than the current power consumption of human civilization. Photosynthetic organisms also convert around 100 to 115 billion metric tons of carbon into biomass per year. Photosynthetic organisms are photoautotrophs, which means that they are able to synthesize food directly from CO2 and water using energy from light. However, not all organisms that use light as a source of energy carry out photosynthesis, since photoheterotrophs use organic compounds, rather than CO2, as a source of carbon. In plants, algae and cyanobacteria, photosynthesis releases oxygen. This is called oxygenic photosynthesis. Although there are some differences between oxygenic photosynthesis in plants, algae, and cyanobacteria, the overall process is quite similar in these organisms. Some types of bacteria, however, carry out an oxygenic photosynthesis, which consumes CO2 but does not release oxygen. Carbon dioxide is converted into sugars in a process called carbon fixation. Carbon fixation is an endothermic redox reaction, so photosynthesis needs to supply both the source of energy to drive this process and the electrons needed to convert CO2 into a carbohydrate. This addition of the electrons is a reduction reaction. In general outline and in effect, photosynthesis is the opposite of cellular respiration, in which glucose and other compounds are oxidized to produce CO2 and water, and to release exothermic chemical energy to drive the organism's metabolism. The two processes take place through a different sequence of chemical reactions, however, and in different cellular compartments. Oceanic carbon cycle. Air-sea exchange of CO2. The Earth's oceans contain a large amount of CO2 in the form of bicarbonate and carbonate ions, much more than the amount in the atmosphere. The bicarbonate is produced in reactions between rock, water, and carbon dioxide. One example is the dissolution of calcium carbonate. CaCO3 plus CO2 plus H2O Ca2 plus 2HCO-3. Reactions like this tend to buffer changes in atmospheric CO2. Since the right side of the reaction produces an acidic compound, adding CO2 on the left side decreases the pH of seawater, a process which has been termed ocean acidification. pH of the ocean becomes more acidic although the pH value remains in the alkaline range. Reactions between CO2 and non-carbonate rocks also add bicarbonate to the seas. This can later undergo the reverse of the above reaction to form carbonate rocks, releasing half of the bicarbonate as CO2. Over hundreds of millions of years, this has produced huge quantities of carbonate rocks. From 1850 until 2022, the ocean has absorbed 26% of total anthropogenic emissions. However, the rate at which the ocean will take it up in the future is less certain. Even if equilibrium is reached, including dissolution of carbonate minerals, the increased concentration of bicarbonate and decreased or unchanged concentration of carbonate ion will give rise to a higher concentration of unionized carbonic acid and dissolved CO2. This higher concentration in the seas, along with higher temperatures, would mean a higher equilibrium concentration of CO2 in the air. Carbon moves between the atmosphere, vegetation, dead and alive, the soil, the surface layer of the ocean, and the deep ocean. Effects of current increase. Direct effects. Radiative forcing drivers of climate change in year 2011, relative to pre-industrial, 1750. Direct effects of increasing CO2 concentrations in the atmosphere include increasing global temperatures, ocean acidification, and a CO2 fertilization effect on plants and crops. Temperature rise on land. Projected temperature and sea level rise relative to the 2000 to 2019 baseline period for RCP climate change scenarios up to 2500. The global average and combined land and ocean surface temperature show a warming of 1.09 degrees Celsius, range 0.95 to 1.20 degrees Celsius, from 1850 to 1900 to 2011 to 2020, based on multiple independently produced datasets. The trend is faster since 1970s than in any other 50-year period over at least the last 2,000 years. Most of the observed warming occurred in two periods, around 1900 to around 1940 and around 1970 onwards. The cooling/plateau from 1940 to 1970 has been mostly attributed to sulfate aerosol. Some of the temperature variations over this time period may also be due to ocean circulation patterns. Temperature rise in oceans. It is clear that the ocean is warming as a result of climate change, and this rate of warming is increasing. The global ocean was the warmest it had ever been recorded by humans in 2022. This is determined by the ocean heat content, which exceeded the previous 2021 maximum in 2022. The steady rise in ocean temperatures is an unavoidable result of the Earth's energy imbalance, which is primarily caused by rising levels of greenhouse gases. Between pre-industrial times and the 2011 to 2020 decade, the ocean's surface has heated between 0.68 and 1.01 degrees C. The upper ocean, above 700 m, is warming the fastest, but the warming trend is widespread. The majority of ocean heat gain occurs in the Southern Ocean. For example, between the 1950s and the 1980s, the temperature of the Antarctic Southern Ocean rose by 0.17 degrees Celsius (0.31 degrees Fahrenheit), nearly twice the rate of the global ocean. Ocean acidification. Ocean acidification is the decrease in the pH of the Earth's ocean. Between 1950 and 2020, the average pH of the ocean surface fell from approximately 8.15 to 8.05. Carbon dioxide emissions from human activities are the primary cause of ocean acidification, with atmospheric carbon dioxide (CO2) levels exceeding 410 ppm in 2020. CO2 from the atmosphere is absorbed by the oceans. This produces carbonic acid, H2CO3, which dissociates into a bicarbonate ion, HCO-3, and a hydrogen ion, H+. The presence of free hydrogen ions, H+, lowers the pH of the ocean, increasing acidity. This does not mean that seawater is acidic yet, it is still alkaline, with a pH higher than 8. Marine calcifying organisms, such as mollusks and corals, are especially vulnerable because they rely on calcium carbonate to build shells and skeletons. A change in pH by 0.1 represents a 26% increase in hydrogen ion concentration in the world's oceans. The pH scale is logarithmic, so a change of 1 in pH units is equivalent to a tenfold change in hydrogen ion concentration. Sea surface pH and carbonate saturation states vary depending on ocean depth and location. Colder and higher latitude waters are capable of absorbing more CO2. This can cause acidity to rise, lowering the pH and carbonate saturation levels in these areas. Other factors that influence the atmosphere-ocean CO2 exchange, and thus local ocean acidification, include ocean currents and upwelling zones, proximity to large continental rivers, sea ice coverage, and atmospheric exchange with nitrogen and sulfur from fossil fuel burning in agriculture. CO2 fertilization effect. The CO2 fertilization effect or carbon fertilization effect causes an increased rate of photosynthesis while limiting leaf transpiration in plants. Both processes result from increased levels of atmospheric carbon dioxide, CO2. The carbon fertilization effect varies depending on plant species, air and soil temperature, and availability of water and nutrients. Net primary productivity, NPP, might positively respond to the carbon fertilization effect. Although, evidence shows that enhanced rates of photosynthesis in plants due to CO2 fertilization do not directly enhance all plant growth, and thus carbon storage. The carbon fertilization effect has been reported to be the cause of 44% of gross primary productivity, GPP, increase since the 2000s. Earth system models, land system models, and dynamic global vegetation models are used to investigate and interpret vegetation trends related to increasing levels of atmospheric CO2. However, the ecosystem processes associated with the CO2 fertilization effect remain uncertain and therefore are challenging to model. Terrestrial ecosystems have reduced atmospheric CO2 concentrations and have partially mitigated climate change effects. the response by plants to the carbon fertilization effect is unlikely to significantly reduce atmospheric CO2 concentration over the next century due to the increasing anthropogenic influences on atmospheric CO2. Earth's vegetated lands have shown significant greening since the early 1980s, largely due to rising levels of atmospheric CO2. Theory predicts the tropics to have the largest uptake due to the carbon fertilization effect, but this has not been observed. The amount of CO2 uptake from CO2 fertilization also depends on how forests respond to climate change, and if they are protected from deforestation. Other direct effects. CO2 emissions have also led to the stratosphere contracting by 400 meters since 1980, which could affect satellite operations, GPS systems, and radio communications. Indirect effects and impacts. Some climate change effects, clockwise from top left: wildfire caused by heat and dryness, bleached coral caused by ocean acidification and heating, coastal flooding caused by storms and sea level rise, and environmental migration caused by desertification. Climate change affects the physical environment, ecosystems, and human societies. Changes in the climate system include an overall warming trend, more extreme weather, and rising sea levels. These in turn impact nature and wildlife, as well as human settlements and societies. The effects of human-caused climate change are broad and far-reaching. This is especially so if there is no significant climate action. Experts sometimes describe the projected and observed negative impacts of climate change as the climate crisis. Overview of climatic changes and their effects on the ocean. Regional effects are displayed in italics. There are many effects of climate change on oceans. One of the main ones is an increase in ocean temperatures. More frequent marine heat waves are linked to this. The rising temperature contributes to a rise in sea levels. Other effects include ocean acidification, sea ice decline, increased ocean stratification, and reductions in oxygen levels. Changes to ocean currents, including a weakening of the Atlantic meridional overturning circulation, are another important effect. All these changes have knock-on effects which disturb marine ecosystems. The main cause of these changes is climate change due to human emissions of greenhouse gases. Carbon dioxide and methane are examples of greenhouse gases. This leads to ocean warming, because the ocean takes up most of the additional heat in the climate system. The ocean absorbs some of the extra carbon dioxide in the atmosphere. This causes the pH value of the ocean to drop. Scientists estimate that the ocean absorbs about 25% of all human-caused CO2 emissions. Approaches for reducing CO2 concentrations. Carbon dioxide has unique long-term effects on climate change that are nearly irreversible for 1,000 years after emissions stop. Zero further emissions. The greenhouse gases methane and nitrous oxide do not persist over time in the same way as carbon dioxide. Even if human carbon dioxide emissions were to completely cease, atmospheric temperatures are not expected to decrease significantly in the short term. This is because the air temperature is determined by a balance between heating, due to greenhouse gases, and cooling due to heat transfer to the ocean. If emissions were to stop, CO2 levels and the heating effect would slowly decrease, but simultaneously the cooling due to heat transfer would diminish, because sea temperatures would get closer to the air temperature, with the result that the air temperature would decrease only slowly. Sea temperatures would continue to rise, causing thermal expansion and some sea level rise. Lowering global temperatures more rapidly would require carbon sequestration or geoengineering. Various techniques have been proposed for removing excess carbon dioxide from the atmosphere. Carbon dioxide removal, CDR, also known as carbon removal, greenhouse gas removal, GGR, or negative emissions, is a process in which carbon dioxide gas, CO2, is removed from the atmosphere by deliberate human activities and durably stored in geological, terrestrial, or ocean reservoirs, or in products. In the context of net zero greenhouse gas emissions targets, CDR is increasingly integrated into climate policy as an element of climate change mitigation strategies. Achieving net zero emissions will require both deep cuts in emissions and the use of CDR, but CDR is not a current climate solution. in the future, CDR may be able to counterbalance emissions that are technically difficult to eliminate, such as some agricultural and industrial emissions. Concentrations in the geologic past. CO2 concentrations over the last 500 million years. Concentration of atmospheric CO2 over the last 40,000 years, from the last glacial maximum to the present day. The current rate of increase is much higher than at any point during the last deglaciation. Carbon dioxide is believed to have played an important effect in regulating Earth's temperature throughout its 4.7 billion year history. Early in the Earth's life, scientists have found evidence of liquid water indicating a warm world, even though the sun's output is believed to have only been 70% of what it is today. Higher carbon dioxide concentrations in the early Earth's atmosphere might help explain this faint young sun paradox. When Earth first formed, Earth's atmosphere may have contained more greenhouse gases and CO2 concentrations may have been higher, with estimated partial pressure as large as 1,000 kilopascals, 10 bar, because there was no bacterial photosynthesis to reduce the gas to carbon compounds and oxygen. Methane, a very active greenhouse gas, may have been more prevalent as well. Carbon dioxide concentrations have shown several cycles of variation from about 180 parts per million during the deep glaciations of the Holocene and Pleistocene to 280 parts per million during the interglacial periods. Carbon dioxide concentrations have varied widely over the Earth's 4.54 billion year history. It is believed to have been present in Earth's first atmosphere, shortly after Earth's formation. The second atmosphere, consisting largely of nitrogen and CO2, was produced by outgassing from volcanism, supplemented by gases produced during the late heavy bombardment of Earth by huge asteroids. A major part of carbon dioxide emissions were soon dissolved in water and incorporated in carbonate sediments. The production of free oxygen by cyanobacterial photosynthesis eventually led to the oxygen catastrophe that ended Earth's second atmosphere and brought about the Earth's third atmosphere, the modern atmosphere, 2.4 billion years before the present. Carbon dioxide concentrations dropped from 4,000 parts per million during the Cambrian period about 500 million years ago to as low as 180 parts per million during the Quaternary glaciation of the last 2 million years. Drivers of ancient Earth's CO2 concentration. On long timescales, atmospheric CO2 concentration is determined by the balance among geochemical processes including organic carbon burial in sediments, silicate rock weathering, and volcanic degassing. The net effect of slight imbalances in the carbon cycle over tens to hundreds of millions of years has been to reduce atmospheric CO2. On a timescale of billions of years, such downward trend appears bound to continue indefinitely as occasional massive historical releases of buried carbon due to volcanism will become less frequent, as Earth mantle cooling and progressive exhaustion of internal radioactive heat proceed further. The rates of these processes are extremely slow, hence they are of no relevance to the atmospheric CO2 concentration over the next hundreds or thousands of years. Photosynthesis in the geologic past. Over the course of Earth's geologic history, CO2 concentrations have played a role in biological evolution. The first photosynthetic organisms probably evolved early in the evolutionary history of life and most likely used reducing agents such as hydrogen or hydrogen sulfide as sources of electrons, rather than water. Cyanobacteria appeared later, and the excess oxygen they produced contributed to the oxygen catastrophe, which rendered the evolution of complex life possible. In recent geologic times, low CO2 concentrations below 600 parts per million might have been the stimulus that favored the evolution of C4 plants, which increased greatly in abundance between 7 and 5 million years ago over plants that use the less efficient C3 metabolic pathway. At current atmospheric pressures, photosynthesis shuts down when atmospheric CO2 concentrations fall below 150 ppm and 200 ppm, although some microbes can extract carbon from the air at much lower concentrations. Measuring ancient Earth CO2 concentration. Over 400,000 years of ice core data, graph of CO2, green, reconstructed temperature, blue, and dust, red, from the Vostok ice core. Correspondence between temperature and atmospheric CO2 during the last 800,000 years. The most direct method for measuring atmospheric carbon dioxide concentrations for periods before instrumental sampling is to measure bubbles of air, fluid or gas inclusions, trapped in the Antarctic or Greenland ice sheets. The most widely accepted of such studies come from a variety of Antarctic cores and indicate that atmospheric CO2 concentrations were about 260 to 280 ppm immediately before industrial emissions began and did not vary much from this level during the preceding 10,000 years. The longest ice core record comes from East Antarctica, where ice has been sampled to an age of 800,000 years. During this time, the atmospheric carbon dioxide concentration has varied between 180 and 210 ppm during ice ages, increasing to 280 to 300 ppm during warmer interglacials. Carbon dioxide mole fractions in the atmosphere have gone up by approximately 35% since the 1900s, rising from 280 parts per million by volume to 387 parts per million in 2009. One study using evidence from stomata of fossilized leaves suggests greater variability, with carbon dioxide mole fractions above 300 ppm during the period 7 to 10,000 years ago, though others have argued that these findings more likely reflect calibration or contamination problems rather than actual CO2 variability. Because of the way air is trapped in ice, pores in the ice close off slowly to form bubbles deep within the firn, and the time period represented in each ice sample analyzed. These figures represent averages of atmospheric concentrations of up to a few centuries rather than annual or decadal levels. Ice cores provide evidence for greenhouse gas concentration variations over the past 800,000 years. Both CO2 and CH4 vary between glacial and interglacial phases, and concentrations of these gases correlate strongly with temperature. Direct data does not exist for periods earlier than those represented in the ice core record, a record that indicates CO2 mole fractions stayed within a range of 180 ppm to 280 ppm throughout the last 800,000 years, until the increase of the last 250 years. However, various proxies and modeling suggests larger variations in past epochs. 500 million years ago, CO2 levels were likely 10 times higher than now. Various proxy measurements have been used to attempt to determine atmospheric carbon dioxide concentrations millions of years in the past. These include boron and carbon isotope ratios in certain types of marine sediments, and the number of stomata observed on fossil plant leaves. Phytane is a type of diterpenoid alkane. It is a breakdown product of chlorophyll and is now used to estimate ancient CO2 levels. Phytane gives both a continuous record of CO2 concentrations, but it also can overlap a break in the CO2 record of over 500 million years. 60 to 5 million years ago, atmospheric CO2 concentration continued to fall after about 60 million years ago. About 34 million years ago, the time of the Eocene-Oligocene extinction event and when the Antarctic ice sheet started to take its current form, CO2 was about 760 ppm, and there is geochemical evidence that concentrations were less than 300 ppm by about 20 million years ago. Decreasing CO2 concentration, with a tipping point of 600 ppm, was the primary agent forcing Antarctic glaciation. Low CO2 concentrations may have been the stimulus that favored the evolution of C4 plants, which increased greatly in abundance between 7 and 5 million years ago. 200 to 400 million years ago, there is evidence for high CO2 concentrations of over 3,000 ppm between 200 and 150 million years ago, and of over 6,000 ppm between 600 and 400 million years ago. Indeed, higher CO2 concentrations are thought to have prevailed throughout most of the Phanerozoic Eon, with concentrations 4 to 6 times current concentrations during the Mesozoic era, and 10 to 15 times current concentrations during the early Paleozoic era until the middle of the Devonian period, about 400 million years ago. The spread of land plants is thought to have reduced CO2 concentrations during the late Devonian, and plant activities as both sources and sinks of CO2 have since been important in providing stabilizing feedbacks. Earlier still, a 200 million year period of intermittent, widespread glaciation extending close to the equator, snowball Earth, appears to have been ended suddenly, about 550 ma, by a colossal volcanic outgassing that raised the CO2 concentration of the atmosphere abruptly to 12%, about 350 times modern levels, causing extreme greenhouse conditions and carbonate deposition as limestone at the rate of about 1 mm per day. This episode marked the close of the Precambrian Eon and was succeeded by the generally warmer conditions of the Phanerozoic, during which multicellular animal and plant life evolved. No volcanic carbon dioxide emission of comparable scale has occurred since. In the modern era, emissions to the atmosphere from volcanoes are approximately 0.645 billion tons of CO2 per year, whereas humans contribute 29 billion tons of CO2 each year.